All right, 9.60. I think on my answer sheet I said I'd do this on the iPad. I picked this one because I think that it's a little tricky in the wording. And I know you've seen this mechanism before, but I just want to be clear about some of the language that they use. This is another stratosphere gas phase problem where we look at ozone decomposition. And this two-step mechanism asks us to find the expression that shows a second order dependence of ozone on the decomposition. I think that that's kind of a odd way to word it. I think it's better to say asking us to get a rate of reaction expression in terms of the decomposition of ozone. You might remember that when we learned differential rate laws, we said that we could write it in terms of a product growing in or a reactant going away. And you needed a negative sign in front of the reactants going away because the differential is negative in and of itself. But rates of reaction are always positive. So if they're always positive, I need a negative sign to make up for the negative differential. That can make the math a little confusing though, but if we're looking at the rate of reaction, we have the first step in the pre-equilibrium has the rate going forward is equal to that. Then we need to account for the reverse step. And add the second step. So this expression is a representation of this mechanism in terms of the rate of reaction. Now the steady state approximation is looking at what happens to the oxygen atom over time. The oxygen is going to grow in with the first step and be consumed in the reverse, and also the second step. Okay. Isolating oxygen atom, or isolating the intermediate, is going to allow us to develop a term that will give a substitution complying with the rule that we can't allow an intermediate in the overall rate expression. So there's the term for the intermediate that needs to be substituted into our overall rate law. I think we're really going to be in for it here. Let's see. The rate of the reaction, which this problem is again worded as the rate of decomposition of ozone in terms of the rate of decomposition of the ozone, is going to be this first term, and then something that looks pretty messy. I've got K minus 1 times K1. I have oxygen and ozone over K, is this a minus 1? Yes, minus 1 times oxygen plus K2 times ozone. And then this term is going to look pretty ugly. Have K1 in there, another ozone, and then the denominator. I'm going to spare you the thing that makes this much uglier. I actually need to multiply this first term in the form of 1, this as a numerator and denominator. But ultimately, it does simplify down to this. And this is really what we're after, trying to mimic, or I shouldn't say mimic, but try to come up with a rate law expression which corresponds to the experimental observations. If the second step is slow, if second step is slow, that's going to be the rate determining step, then things become second order in ozone, first order in negative first order in the oxygen. So if the second step is slow, essentially what we're saying is that the K2 is much, much less than the K minus 1, then the second term goes away in this expression. What that means is that the increase, if that were to happen, increase in oxygen inhibits this reaction. Which is one of the steps that was mentioned, one of the experimental observations that was made, and also that it's second order in ozone. So this rate law expression does correspond to that under these conditions of the second step being slow. All right, I hope this helped. See you soon.